Today we will see how to check the nozzle loads. So already we have checked the stress summary and restraint summary and the displacement summary. So now we will see how to check the nozzle loads. Okay, we'll continue the same model. So once we complete the restraint summary check, if all the supports are taking load and your displacements are within the allowable and your nozzle loads, your stresses are within the allowable, then we'll go to check the nozzle load. So first we'll check the nozzle load for the pumps. Okay. So generally for the pumps, we'll check the nozzle load at this point only. Okay, already we have discussed that one. So we are going to check the nozzle loads at this location for the discharge line, and for the suction line, this location at the suction nozzle we are going to check. Okay. So for this, first we need to see how to enter the values, or first we will make a table on the Excel sheet, or you can make your nozzle limit check. One option is there. So you can either give the nozzle limit check here, or you can make on Excel sheet like this. Okay. So first we will see how to make this Excel sheet. Okay. Then only it is easy for us to compare the values. Okay. First we will see this Excel sheet, then we'll go for nozzle limit check. Okay. So we will see today how to prepare the Excel sheet. First we need to open the vendor drawing of the equipment. So this is our pump vendor drawing. Our N1 nozzle is our suction nozzle. First we'll go to suction. So N1 is our suction nozzle, 4-inch 300 rating. And the allowable loads. First you need to check the allowable loads. So this is the allowable forces and moments provided in the vendor drawing. Okay. So in this, you can see Fx, Fy, Fz for suction nozzle, Fx, Fy, Fz, and Mx, My, Mz. Okay, they're given like this. So these forces, and we need to first compare the axis. For example, this is your suction axis. You need to see what is your CAESAR axis. The CAESAR axis for suction nozzle, is the pump which is in X direction. Okay, if you see, this is your X direction. So just copy this axis from here, and you can just paste it here. Okay. So now our axis, our pump axis, suction axis is X axis as per CAESAR file. But if you check the vendor drawing, they given this is their axis. This is pump suction axis. So both are matching because your pump axis is suction axis is X, and CAESAR axis also X. So both are matching. Then your Fx value as per CAESAR and as per CAESAR and as per the vendor drawing is same. So you can consider the same value of Fx. Okay. And then if you check the Y direction, means the vertical. So our vertical is in Y direction, but if you check here, it is in Z direction. So what does it mean? Means their vendor drawing Fz is equivalent to our Fy. So here already I made this one. So CAESAR2 model x-axis is equivalent to vendor drawing x-axis. That is matching. But if you check Y, vertical load is they given us Z. Okay. So that means their Fz is equivalent to our Fy. Understood, no? And other axis is this axis. This axis is Z axis. So if you know these two axes, then other axis remains same. Means the remaining axis will be Fy. So Fy vendor drawing Fy is equal to our Z axis. Okay. So like this you have to make. Uh, uh, so you have to compare correctly. Then only you will get correct results. Okay. But if you are using resultant forces, what is resultant forces means square root of fx square plus fy square plus fz square. If you check this formula, so square root of c6, this is c6 square and d6 square and then a6 square. So sum of square root of fx square plus fy square plus fz square. So what we need to do, we need to write the correct value here. How to write? So we'll copy this. Okay. So I'm going to delete this one and we'll see how to enter the values here. Okay. So first we need to check the values. So what we have done, there fx equal to fx vendor drawing equal to CAESAR fx. C. Just give C. Okay. That means 10235 to write 10235 exact value, the same value has to be entered here. Then if you take fy here, this fy is equivalent to this is their fy. So this is our x. So this is our x and this is our y. Vertical is our y. Okay. And one more axis is our z. Okay. Then fx is this one equivalent to x and fy. Their fy is equivalent to our z. So whatever value they are given in fy, it should be entered in fz. Okay, that means 6007. Sorry, and fz. Their fz is this is their fz. It is equivalent to our y. So whatever value given in fz, it should enter in 6675. Okay, like this only we need to transfer the loads here. Then coming to moment, so moment also same only. Okay, so whatever given value given in x direction, so is x equal to same vendor drawing x and CAESAR axis x is same. So that's why we entered the same value. And if you check MY, so MY is 420. So vendor drawing MY is equivalent to our MZ. So we have to enter that value in MZ. Then there MZ, vendor drawing MZ is equivalent to our MY. We have to enter that value in MY. Okay, so like this you need to enter the value correctly. So this pump vendor, like this you can make anything. Okay, so just reference, this is pump tag number and what is the line size and rating, nozzle number, section. So allowable loads we are considering from the vendor drawing. If allowable loads, if they are not provided in the vendor drawing, then what we need to do? We need to check in our design basis. So generally in design basis, they used to give allowable loads. So say for if they are not provided for the pumps, then you have to refer APA 16. if it is for the centrifugal pump. Okay, if it is for the centrifugal pump, then you have to refer APA 16. In APA 16, you will have allowable loads. So that allowable load you have to compare. Okay, then this is for APA pumps and for the static equipments. So for the static equipment, they used to give you have to refer. They used to give this table. For example, let's see, tank nozzle load special shells, and this is for 8 exchanger. So for this static vessels, based on the rating, they used to give the values FA, FL, FC, FML, MT like this. So forces and moments they used to give. I will tell you what is FA, FL. That I will explain you while checking the load for the static equipment. We'll see it later. Okay. Okay, so these are the allowable loads. So if for centrifugal compressors, for example, if a line is connected to your centrifugal compressors, then if they are not provided allowable load, then you go for APA 617 or annexure 2E. That is 2 times of APA 617 annexure 2E, or you can check with NEMO SM23. Okay, and for the rotary pumps, you have to refer APA 619. And or for the positive displacement pumps, you have to refer APA 676 2 times. Generally, they used to give 1 time, 2 times, or 3 times like that. So you have to follow this one. You have to check the vendor drawings correctly. So, so all pump vendor drawings or any equipment vendor drawings, it will be come for piping stress review. So the engineer who is reviewing the vendor drawings has to check all the details like nozzle loads. First is nozzle size and rating, and the nozzle forces and moments, if whether they are given correctly or not, whether they are followed as per the specification or not. For example, if in the specification, if you are using, if you are getting APA 676 pump, so they given 1 time of APA 676 means you have to comment in such a way that please refer the specification or this number and change the allowable loads to 2 times of AP 619 676 table 2. So you have to comment like that. Okay. So for all equipments, they used to give the table, which table they have to refer, and what is the multiplication factor to be followed. Okay, that you have to check your stress design basis. Okay, and also, yeah, 1 minute, I will open this one. So now we enter the suction nozzle value, and if you will see for the discharge nozzle also, we will enter the value. Okay, just so we'll copy this same thing. What we will do, we'll paste it here. Okay, so now for this 3A pump, what is your discharge nozzle number? It is 5000. So you change that one. Node number is 5000. Okay, and you have to compare the allowable loads here. Vendor drawings. Okay. So for discharge, you have to refer this second table. Okay. So you have to check the units also. Unit should be correct. Newton and Newton meters. In some project, they used to give kg or kg meter like that, or Newton mm also they used to give sometimes. So you have to refer in a correct way. So here, what is the discharge nozzle size? It is 3 inch. Okay. So what is our discharge nozzle size here? Discharge is N2 3 inch 380. So we have to write range, regenerating and 2. Change this one to discharge. Okay. Go to here, same thing, because the axis they followed the same axis only. So then whatever followed for the suction, we have to follow the same axis here, because for x-axis is for suction axis only. So it is same only. So for this one also, this x is matching. So whatever they are given, 6230 is, you have to write 6230. Okay. And then what is their FY? Their FO is here. That means our Z axis means 6007 should be entered. 1 minute, I will in Z axis. Okay. So I will delete all the things. And FZ. FZ, what is their FZ? FZ is vertical. That means our Y axis. So FZ is equivalent to 14462 is equivalent to our FY. Okay. And then MX. Their MX 1628 because X axis is same. MO is 1980. So their Y axis is equivalent to our Z axis. So 1980 here to enter it in MZ. Okay, and M remaining is MZ. So their MZ is our MY 936. Okay, like this we have to enter. First you have to enter the allowable loads. Then we will compare the output of CAESAR and we will paste the value here and I need to compare the loads. Okay. So we'll check how to compare the loads. First we'll see the pumps, then we'll see the uh, static equipment. Okay. So now generally for rotating equipments, just we'll run this one. Okay. So what are all the load cases to be considered for the qualification of nozzles for rotating equipment? So generally for the rotating equipments in design basis itself, they used to give. So in all other projects, what we are doing means we'll check only the maximum operating temperature case and working and standby case, and also the sustain case. Okay. For you see, what we are going to consider, if you check some of the design basis they used to give. You see, nozzle loads for the pumps. Not for the pumps, not only for the pumps. For the rotating equipments can be evaluated at operating temperature if the load calculated at the design temperature exceeds the standard allowable. So in this project, what they are asking us to do, first we need to check the design case also. If it exceeds, then you have to go for operating temperature. But generally for rotating equipments, we will check for maximum operating temperature only. We will check other. So, yeah, you say in earthquake case, rotatory strain sensitive equipment loads will not be qualified. So we should not include other wind and seismic in the qualification of rotating equipment. So you have to remember that what we have to consider. We need to consider T2. T2 means maximum operating temperature. Then T4 and T5 is working standby temperature, and then your sustain case. These cases are enough for the nozzle load checking of rotating equipments. Okay, rotating equipments in this sense, pumps, compressors, turbines, and all. Okay, you have to consider operating temperature and working and standby temperature case and sustain case. You select this one and select restraint summary extended wave reports. This is universally followed, okay. But if client asks us to consider design temperature also, then you have to consider design temperature. This case also L2. Okay, now we are considered L4, L6, L4, L8, L10, and then L22 and L23. Okay, so that's why I have written here also L4, L8, L10, L22, and L23. Okay, so you select restraint summary extended and go to our nozzle. Means our nozzle is 1270. Find in the report. You see, here is this option. If you check this one, select this, and you can find the node number 1270. To type here, then it will go to the particular node. Okay. So here the values given already. I copied the values. So what we'll do? Let's see, okay, we'll delete these values here. So now you have to take the maximum value. Okay, this will show here. This is our nozzle 1270. Will show case by case. Fx this much loads is coming in this case. Okay, and the maximum loads on in fx direction is 6063, 6033. So no need to worry about this one. So you consider the maximum value. Just select all this value like this. Control C and paste it here. Okay. Then you select the moments and paste it here. So here, since the load case 10, this and all there, the value is not coming. So what we have to do? Control F and then replace the value with this. Replace all. Then you will get the real value. Or you can enter manually also. 6033. Just enter manually also. You can do anything you can. So now we are going to compare the values. Fx. What is your Fx? So our allowable load is 10,000 to 35. And whatever loads we are getting from CAESAR output is 6,033. So if our load is, CAESAR output load is lesser than your allowable load, then this direction is okay. The loads, the forces in X direction, it is within the limit. Okay. You compare this one. So irrespective of the sign, you just compare in order to consider the sign here, positive or negative, no issue. Okay. So in FI, allowable load is 6615, and whatever we are getting is 1223. So it is lesser than the allowable load. And FZ also, it is lesser than the allowable. So obviously, if your individual forces are within the limit, your resultant forces also within the limit only. Okay. Then if you go to check the moments, moment along x-axis. So your allowable load is 1763 and whatever you are getting is 48. So it is okay. Moment along y-axis. So if moment is 420 and whatever we are getting is 800. That means where allowable loads are exceeding. Okay, now we'll see how to tackle that one. Then MZ. In MZ direction, allowable load is 420 and whatever we are getting is 380. Okay, so this is also okay. If it is 419 also, it is okay. Okay, and resultant. So in the resultant, whatever values you are getting is okay. Is lesser than the allowable load. That means okay. Here it is okay. So what we will do in this case, no? If it is qualified by resultant, okay, it is qualified by resultant moments we are given. The individual moment is failing in my direction, in y direction. Okay, but it is qualified in resultant. Okay, so you need to inform this one to your vendor or your client. Okay, so if they are accepted, then we can leave like this. So whatever loads were provided, that is okay. So if they are not accepting, then what we need to do? We need to try to qualify the moments. How to qualify the moments, we'll see. Okay. Then we'll check the discharge. This is discharge line. What is the node number? 5000. We'll enter the value, then we'll see. Go to 5000. Just copy this value and moment also you copy it. Okay. So find and replace. Now you can see FX. It is within the allowable. Just select here, and FO is force also within the allowable. It is lesser than the allowable load, and FZ it is within the allowable. Okay. And your resultant also it is within the allowable. And MX, what is MX? Oh, MX also within the allowable. And MY also it is within the allowable. You can change this one to black. Sorry. And MZ also within the allowable. So your discharge nozzle is qualified. Okay. So discharge nozzle is completely qualified. So your suction nozzle is exceeding in one direction of moment. So we will see. Okay. So like this only you need to check the allowable loads for the pumps. So now we will see how to check the allowable loads for the static equipment. Okay. Then we will see how to use the nozzle limit check. Then how to qualify the nozzles. I will tell you. Okay. So we'll go back to the model. Okay. And same thing you need to check for the other two nozzles also. Okay. And for the static equipment, if you check for the static equipment, so here only we need to check the nozzle load for the static equipment. So in this case, I will open the vendor drawing of this static equipment. Okay, so this is a vendor drawing of this equipment. Okay. So where is our nozzle? This is our nozzle, and what is our nozzle? So our nozzle number is N14, I think so. Or we need to check the isometric drawing for the correct nozzle number. Let's see if the isometric drawing, if you check. So it is N6, sorry. It is N6. Where is our N6? N6 is here. Okay. So this is our nozzle. Okay. So what we will do again, we'll make a table like this. So enter the equipment tag number here, and nozzle number is N6. So in the N6, 6-inch 150 rating, it is 150 rating. 6-inch 150 rating, and then you have to compare you have to enter the values from vendor drawing. So here we need to check where are the allowable loads. Yeah, you see here admissible load they given. So this is your allowable load, and your line size is, or nozzle size is 6-inch. So go to 6-inch. This is our Okay, these are our loads fx, fy, fz, and mx, my. Okay, so in this case, what we need to do, we need to compare fx. First, we need to check the axis, CAESAR axis of our. Okay, so what is our, first we need to check what is our nozzle axis. That is very important. Okay, so our nozzle axis, if you go to top view, you'll come to know. So our nozzle axis is it's a skewed one, not a regular one. Means not in any of the axes. It is going in two axes. In x-axis as well as in z-axis, x and z. So maximum is it is going in x-axis, minimum is z-axis. Okay. So now what we need to do, we need to first we need to see how we can do. You can, for this skewed nozzles, we have to rotate this. First you have to rotate the model to any one of the axes. Okay. So if you go to top view, so this nozzle is in two axes, x and z axis. So first we need to find the angle to rotate this entire model into one axis in order to get the force in that particular direction. Okay. So for this we need to find out the angle. So you can easily find out the angle by a trigonometry formula, or you just draw one like this. So then you can find out this angle easily. Okay. You can do either using AutoCAD like what we have drawn. For example, just I took this value, only one, this is axis 214 mm. Just I have drawn on 214 mm here, and another direction is 123.4, 123 mm. So I drawn 123 mm. Then I connected this with this line. Okay, so first I drawn this one and this one and connected with this line. Okay, so if we measure this one, we're getting this angle 30 degrees. So you can do like this also. If you have AutoCAD, you can do like this. Or directly, if you want to do calculate the value limits, you have to see the cosine value. So whatever they given is cosine is 0.86. So if you want to check the angle means it should be cosine 1 by cos theta. I mean theta equal to cos inverse. So if you check the inverse of cosine value, then you will get the angle. So for that, and uh, if you check inverse cosine calculator is will be there. For this, you have to enter this value 0.866. If you enter 0.686, you will get the degree. You can angle the, you can check the angle or can calculate the angle like this. Okay, so our angle is in 30 degree. So like this you can find the angle in either way. Okay, so if you find the angle, then what we need to do, we need to select all the equipment, all the model, and right click, or if you go to here, just go to input listing element, same thing. No, I think select all, it got selected. You see, right click, block operation, rotate, and you are going to rotate in y axis. So our angle is 30 degree only. I mean, you want to align this with this degree, so it should be rotating in this direction. So if you want to rotate this direction means You have to give minus here. Minus advance means advance minus 30 degree. If you're giving minus 30 degree, then you see it is getting aligned in x-axis. Okay. So now we'll see if you are giving plus 30 means it will go in the opposite direction. Block operation, rotate, minus 30. Minus 30 means go in the opposite direction. Sorry, minus 30, 1 minute. It's not getting rotated. 1 minute. Elements. Select all the elements. Block operation, rotate, y-axis. Having 30 degree means, yeah, you see it is not aligned with your x-axis. It is going in opposite direction. Means it is rotated like this. It is going like this. So instead of this, what you have to give? You have to give minus 30 degree one. Then only our axis will be aligned with the x-axis. So we'll see. Right click, block operation, rotate axis and minus 30. Now you see it is aligned with x-axis. Okay. So based on this, what we have to do? We will enter the allowable loads table here. We'll compare. So what is our x-axis and what is the one minute, I will open the vendor drawing once again. Okay, here. So here this is the axis for the equipment provided in the vendor drawing. So you need to compare with our value. Okay. So for this you open the Excel sheet. So in this case they given for generally for static equipment they will not give X, Y, Z. They used to give axial force or radial force, longitudinal force, and circumferential force. I will show you in the next equipment vendor drawing how to compare the longitudinal force and the axis provided in the vendor drawings and with respect to our CAESAR axis. Okay. Now we will see in this particular calculation. So in this vendor drawing, they are given X, Y, Z axis. First we will see. So our nozzle is in Z direction, X direction. As per CAESAR, it is in X direction. So that means our x-axis is equivalent to their z-axis. That you have to write. Okay. So here what we'll do, we'll write here x equal to x equal to z. Okay. So whatever value given in z, it is equivalent to x. Left side is our axis, right side is vendor axis. So y direction is over y and their y it is matching. So y equal to y. Okay. Then z. So just write here vz for better understanding. Vendor. Oh, okay. And z axis is our x axis. Correct? No. Our z axis is in their x axis. So with this, what we'll do, we'll write down the values in our Excel sheet. Okay. Fx, what in our Fx means their F is it. What is their F is it? 1500. You enter 1500 here. Okay. And Fy. So Fy is equivalent to their Fy. So whatever given in y direction, you have to write it here. And Fz. So our Fz is equivalent to their Fx. That means 5538 is their Fx. You have to write 5538. Sorry, 5538. So here resultant also we given, they have not provided any resultant value, just for our understanding and to request the vendor, we have used this resultant forces. For moment also same thing, resultant moment will be there. Okay. So now we will go to moments. So moments, mx, our mx is equivalent to their mz. That means mz is 4072, and MOE is equivalent to their MOE 1744, and our MZ is equivalent to their MX, that is 494. Okay, so this is the value we are getting, and moment also square root of mx square plus my square plus mz square. Okay. So now we'll see. Now we'll go to the CAESAR model and we'll take the value. Now we rotated the model. Okay, just run the model. So here we need to enter the collect values. Okay. So the next step we will see how to enter longitudinal force, circumferential force, and axial forces with respect to our nozzle. You have to remember that one. Okay. So for I told for static equipment you have to consider design temperatures as well as all the wind cases and seismic cases. So we'll consider all the cases, all operating cases and sustained cases. For rotating equipments, we will not consider the occasional cases, wind and seismic. But for static equipment, we need to consider all the cases. Okay. And select restraint summary and go to view reports. Okay. If you want to filter, you can filter. If you want to see only this nozzle. So what is our nozzle? First we'll see. It's given us 11030. Okay. So if you want to filter, you can filter here. Go to filter. In filter, you just type 11030, 11030. Just apply. So it will show only that particular node. If you enter that one, or if you want a set of nodes from 11330 to till end, or 10 to 50, like that. So any range you can keep. Okay. So now we have selected only 1133030. So it has shown only 1133030 node number only. So in this also it will show all the loads for different cases. We'll take the maximum of all the cases. Okay. And then you enter here, copy and paste, copy and paste it here. Then you select this row, Control F, replace all. Okay. So now you can compare the values. So our allowable load is 1500, but what we are getting is 12,230. So it is exceeding the allowable. And in FY also, it is exceeding. And in FZ, it is 5538, and whatever we are getting is 2092. So it is qualified. Okay. And in the resultant also, it is exceeding. Moment allowable is 4072, and whatever I getting is 1674. This is within the limit. Okay. And moment 1744, and whatever I getting is more than that. Here also it is exceeding, and in the resultant also it is exceeding. So this nozzle is having, I mean, the nozzle is totally failing, means exceeding the allowable. Whatever loads we are getting, that is exceeding the allowable loads provided by the vendor. That means you have to qualify this one, you have to work it out to qualify the nozzles. So how to qualify the nozzle? There are different methods to qualify the nozzle. Okay. First, if any value, if it is failing, for example, if force is failing in Fx, that means if it is exceeding in Fz, then you have to check. So what we need to do? So Fx means in which direction it is failing, means which sign. So it is in negative direction, means the force is going towards this direction. Okay, because this is in negative. Okay, that means this entire pipe is pushing this one here. So you have to limit that force. If you want to limit the force, what we need to do? We need to change the routing somewhere here, because your movement may be in this direction, it is crossing these forces. So for 1 minute, for this, what we need to do? We need to check the movement. For example, if you check here and go to the deflected shape, go to top view, go to the deflected shape here. You say pipe is expanding towards system here. What we need to do? We need to either add some flexibility. So you can give like this, okay, or you go like this. Sorry, go like this, and you can come. You can add like this flexibility. Okay, so you have to check the 3D model for this. So 1 minute, I will show you the 3D model. You have to check the feasibility of the routing. So you have to try different options. So this is the particular line, the 3D model. See, this is the particular line. So you need to check the space, whether any space is there or not. So if you want to go here and come, for example, if you want to go like this, come like this. So generally, suction side should not have more elbows. Okay, so you have to check with your process team also. If you are adding 1, 2 elbows, okay, so then you have to check with the process team whether it is okay, because there will be a more pressure loss. If you add elbow, then pressure loss will be, I mean, they have to calculate the pressure drop. So they will check. If you add more elbow, then you have to check with your process team for the, mainly for the suction lines. So discharge line, it will have pressure, the fluid will flow based on the pressure itself. But for the suction line, so the flow will be gravity flow only. Means it will be from the top and automatically it will go to the pump. Okay, that is gravity flow. So, but we are not adding any pockets. Pocket means it is going up, down, and again rising up. So this we'll call it as pocket if it is connected to any nozzle pump, suction nozzle. So we should not form any pockets here. Okay. So this we'll call it as pocket. So this you should avoid. So labor team, they will take care of this, but if you're suggesting any routing, if you want to add flexibility, don't do like this. Don't come down and go up. For the suction lines, mainly for any lines. Okay. In this also, we need to check the feasibility. So this is already we have qualified, because we have checked with the process team. So what they suggested, don't add any elbows. So what we did means we have added an expansion joint here. If we check the isometric drawing, we have added an expansion joint because your movement is more here. Okay. So in order to avoid the movement, either you need to add some flexibility somewhere here, or or you can, you can have the flexibility here also, like this somewhere. So, in order to avoid the elbows, what they suggested, since this is a water treatment plant, they suggested use rubber bellow joint or rubber expansion joint. So, if you check the isometric drawing, you will have only bellows here. See, at this location, we have bellows only. So, if you use bellow, then your moment will come down. Either way. So, if you check the, if you add any elbows, it may come down also. So, just we will check. So now we will see how to add the, change the routing, and we will try. Okay. So you can try from your side. Just I will say, we will see whether the loads are coming down or not. Okay. So for this, what we need to do again, we need to rotate this model to the original routing. Right click, rotate, and again if you are going to 30 degree, then it will go back to the original position. Okay. So now what we have suggested, we'll try, because the movement is towards this direction. We will try to add elbow like this or like this also. You can try any options you can try. So what we will do, we'll copy this. Just make it as some options, or try anything you can give. I'm just giving option 2. So you have to understand the concept. Okay. So first we need to check in which direction the forces are exceeding or the moments are exceeding. Okay. If the forces are exceeding, in this case, the forces are exceeding in x direction. So you have to check the movement also, how the pipe behaves. So based on that, you need to take a decision whether routing change is required or not, or how to change the routing. Based on the 3D model also, you have to check. Okay. So in this case, uh, you see, fx is very high. So other two directions we can reduce, but for fx is very high. So that means the next direction only or movement will be there, and that too it's in a negative direction. That this direction. Okay. So what we will do now, we will add some elbows like this. We'll try this option. Okay. First we'll try this option. So I'm going to insert an element here, 152, 160. This is 6-inch line. So 6-inch line, 229 is our elbow arm length. So 229 into 2, 458. Okay, 229 will be our arm length into 2, 458. Plus we make it as 200 mm addition spool, 658. We will make it as 658. But we need to check whether 658 mm is available in the 3D model. That we need to see. Say some pedestal is the y direction. So this is in y direction. Oh, 1 meter is there. Okay. You can go, but here access way is there. That okay, that we'll discuss with our team also. So here access way is there. So you need to see what is the distance. 400 mm only, 424. Okay, first we'll see how to qualify, then we will check other options, when either option is possible or not, because we cannot come here because already this, what is this, dipole kind of thing, some wall is there, so it is there. So I think we cannot go routing like this. We will see. First, we'll check this off. So we have added a spool here and add the elbow. Double click the bend. Go to the next node. So next node should be your 2 node. From that 2 node, it should be here. So now we have added here, and this spool 658 has to be included here also. Okay. 658. I am going to add the same spool. Okay. Now you see it's like a loop. Okay. Like this. We'll try now. Run this system. We'll see. Now what again we need to rotate to check the nozzle loads with respect to this axis. So what we will do, we'll copy this and just note it down. Errors option 2, just for our understanding. Okay. So if you are doing analysis, if you are doing qualification, no, you have to do like this. Then again, what to go to top view. Right click, rotate, minus setting. So now you see it is rotated here. It looks like non-aesthetic, but okay, we'll see. We'll run the system. Select all the operating cases and sustain case also. Okay, say we'll copy and paste it here. We'll see. And here also. Okay. Okay, now you see our forces are come down. I mean, off time it is reduced. Yeah, 50% loads have been reduced. Here it is. This is also reduced. Okay, that means whatever routing we are suggesting, that is okay. But this load is getting increased, but it is still within the allowable load. So we will try to qualify this one with respect to resultant force. If client accepts, then it is good for us. Otherwise, we have to try, because still we need to increase length. But if we check Fy, previously forces along y-axis in positive direction. Okay, so if the loads are in positive direction, that means you have to move the support away from the nozzle. Understood? Because this support is pushing the nozzle towards up. I mean, previously this support is very close to the nozzle. That's why our load is in positive direction. Correct? Now the support has been moved away. So now the load is in negative direction. So if the load is in negative direction, you have to move the support somewhat close to the nozzle. Means not close means you can adjust here. You can move the support. For example, now we'll see. We'll move the support here some 300 mm or 400 mm, 400 mm towards this side. So we will add that 400 mm here. Okay. So now we will see what is the load. Previously it is 1611. So now if you check the loads, we copy this, uh, and we will paste the value here. So each and every time you need to check correctly all the, if you're making any changes, you need to check the stresses, displacement as well as no restraint summary and nozzle. Okay, compared to previously, you see, I moved the support close to the nozzle, means towards the nozzle. So your load has been come down. So that means it is working. Here also an FX direction also it is working. But it is very little impact only, not that much. And there is no change in the moment. Small changes, no issue. Okay. So main thing is the problem here is FX direction. That means you have to increase the length further. Then only our loads will come down. So like this, you need to check for all the cases. Just I'm going to increase some 200 mm again. So slowly you have to increase. Not suddenly can increase 1 meter, 2 meter, not like that. 100 mm, 50 mm, like that only you have to increase and you check the loads. Okay. Okay. Now I increase this length. Sorry. So you can try yourself for other calculations also, okay? Or you can try this calculation. Try different options. This is one of the options. We'll have more options. So you have to try. I will show you how we are qualified. I will show that CAESAR file also. Now you can see. I am copying that one. Okay. So there is little bit changes, but load has been reduced, but only small change. Oh, okay, it is okay. So if you do like this, the other two direction loads are increasing. So I have to check carefully. Okay. So in this case, what we need to do, we need to try to reduce these two loads also. It's FOA and FZ. FOA, it is increased, you see. So if you move that support again close to the nozzle, so this FOA load will reduce. Then you can bring this one below this resultant force. Then it will be okay. But if you check the moment, so moments are still on the higher side only. So what we need to do, if any failure is there in moment, so what is our option is, if the moment is failing in mx, or in this case you say my and mz. So if it is failing in my, then you have to reduce force in other two directions, because moment is force into perpendicular direction. So if it is failing in my, what we need to do? We need to reduce the fx and fz. If it is failing in mz, then you have to reduce the forces in Fx and F1, then automatically your force moment will come down. Or you need to add guides, because there is no guide in this line. So we need to see. First we'll reduce the vertical load now. How to reduce the vertical load? But still it is exceeding only. So we'll see. We have to move that support away close to the nozzle. So like this you have to work it out. So this support is here. Just I am removing this support. I will try to place somewhere here. Okay, I try to place somewhere here. And we'll see what will be the result. Okay. So you have to try different options. It's like within one run you will not get a solution. So you need to try. If you are new to analysis, then it will take more time for you. So if you are an experienced engineer, so you'll get you can qualify in somewhat lesser time. Okay. So now I moved that support. You see the result. Yeah, it is increased. So that's why you have to try correctly. That's why you keep that support there itself. Okay. And you adjust somewhere. It has been increased, and Y load also it got increased. Moment also increase. So this is not a correct one. You check the 3D plot. Got the first one. You see, still the movement is there. That means this leg is not enough. You have to increase the leg further. So it is not at all possible. That's why we have gone for expansion joint. We can go, but this is a structure line, and the process team didn't accept for this much elbow, two additional elbows and this much additional length. Okay, and also space is not available. The access way has been blocked here. So the access way has been blocked. That's why we didn't try this option. We have gone for expansion below. So if space is there, you can try. Okay. I will show you how we have qualified this. So here, if you check, so we have used the expansion joint here. Okay. So this expansion joint, just this is a rubber expansion joint, and this is untied rubber expansion joint. It is not tied one. Okay. There are different types of expansion. So if tie means you will have tie rods like this. Okay. So this is untied only. Since it's a rubber expansion joint, we are just directly modeled like this. I will explain you how to do. I mean how to build the expansion joint in the later class. Okay, how to build the tied expansion joint or untied expansion joint. So how it affects. Okay. So here we have used axial below. That means axial direction. So it will absorb the moment in axial direction. Okay. So whatever moment is coming here, so it will absorb and it will allow only less moment here. Okay. So that's why this load has been qualified in this case. Okay. So in the skewed cases, 1 minute, yeah, in the skewed, for example, here we have applied the equipment nozzle check. I will show you. Okay. So how to apply this one? This is there, no? This nozzle limit check is there. Okay. So this nozzle limit check, we will see first for this equipment. Okay, since we are working on this. So instead of going for this like this, okay, instead of going for the Excel sheet, what we will do, we'll check the nozzle limit check here. Just double click this. I'll remove this one. Okay, I will delete this and again we'll do. Sorry. So we will save a file. Save as. Okay, in the copy itself I will do. Okay, here you select this nozzle, that particular nozzle location, not nozzle, where we are going to check the nozzle node. So at this node number, this double click this nozzle limit check. Okay. Then what we need to check, enter the node number, this particular node, it is 1840. This is your anchor node number, so that's why we are enter that 1840 and comparison method and make it as absolute. If we leave blank, it will consider as absolute only. Then reference vector. Reference vector means what is our equipment vector, direction. So that you have to give 1, mean because x, your equipment is in vertical direction. If your equipment is in horizontal direction, you have to give x. Okay. So some perpendicular direction only you have to give this one, this value, not in the same direction. Okay. And in the case of z, z-axis is not applicable. So our equipment is in vertical direction. That's why I entered y plus 1 in y direction. Then we have to enter the nozzle loads here. Same. So whatever loads is, first is axial, longitudinal, circumferential. Okay, I will tell you. This is okay. So first you have to remember one thing. FL, sorry, FL. This is FL. This is FL, and this is, sorry, 1 minute. This is FA, axial. Second is longitudinal. 1 minute. This is axial. A is there, no? It is axial. Second one is longitudinal. Third is circumferential. So first we have to remember this one. I will explain you. First you should know what is FA, FL, FC, like that. Okay. So if you check this vendor drawings, you will find like this only for the static vessel. For the pressure vessels or heat exchangers, they used to give like this. They will not give directly Fx, Fy, Fz. They used to give longitudinal force, circumferential force, and axial force, and bending moment. This moment is given as circumferential moment, longitudinal, torsional moment. So what is the meaning means? Axial force. What is axial force or radial force? The axis which your nozzle is located, that is called axial force. Okay. That means this in this case it is axial force. And what is longitudinal force is the direction of the equipment, the direction which equipment is located. For example, in this case, it is located in horizontal this direction. This is longitude. The other direction is circumference. Okay. So like this, you have to remember axial forces or direction of the nozzle, and longitudinal forces your equipment direction. The other direction is circumferential force. So you should know the equivalent forces. Fa is equivalent means because of axial force, your torsional moment will be there. Okay. Moment is nothing but force into perpendicular distance. Okay. So Fa is equivalent to mt. Okay, and FL is equivalent to MC. You have to write it down like this. Means FA equal to MT. FL equal to MC. And FC equal to ML. You have to remember. So what is FA mean? Axial tension or compression force. And FL is longitudinal force and C is circumferential force. And MT is torsional moment and MC is circumferential moment and ML is longitudinal moment. Okay. So like this, you need to remember. So in this case, so in the nozzle limit check also, we have to enter in such a way. I will open the nozzle limit check. So this is a nozzle limit check. I just made it into PDF. So what is here? This is FA. Okay. This is FA. Sorry. Okay, we'll make like this. And this is FL. This is FC. Like this, moment also you have to write. So FA equivalent moment is MT. You have to enter MT value here. And here this is this is FL means equivalent is MC. And FC is equivalent is ML. Okay. So like this only you have to enter here. In our case also. So here what we have to enter in A, that is axial force FA. So in our equipment window drawing, they are not given like that. So they given directly the value. Means axial forces here at what they given Z direct. That means 1500 is your axial force. 1500. Okay, next is FL. Correct, no? FL. So FL is your equipment axis. That means equipment axis. What is your equipment axis here? The window drawing, as per this window drawing, equipment axis is x-axis in this case. That means 5538 should be your here FL. So remaining one axis will be your circumferential moment. Understood, no? Circumferential. That you have to enter. Another axis circumferential is this direction. That is your Fy. 1640 will be your circumferential moment. 1640. Okay. Then moment also the same way you have to enter. So FZ means MZ. MZ, what is MZ? 407. You have to enter here 4072. So FL equivalent is MC. FL equivalent is MC. That means in your window drawing, what is FL? X. So Fx is equivalent to Mx, 494. You have to enter here 494. And go to the next node. This one, the remaining axis is MZ 407. Sorry, remaining axis MY. Okay, this direct. That is, what is MY 1744? 1744. So like this only you have to enter this nozzle limit check. Okay. The same way you can enter for the pumps also. Okay. So in this case they have done analysis for the suction lines only, not for the discharge nozzle. They were not included in this system. That will be a separate system. Okay. So here in this nozzle, in this case also, you have to double click this nozzle limit check and go to your weather drawing, pump weather drawing. Okay. So go to this pump weather drawing. So in pump weather drawing also, generally they used to give Fx, Fy, Fz. They will not give axial, longitudinal, circumferential and all for the pumps. For the static equipments only, they used to give axial, longitudinal, circumferential. Okay. So what we need to do here, Fx. First we need to check axial direction, Fa. So Fa is nothing but your nozzle direction. So nozzle direction is X direction. So X direction is this is a suction nozzle. So I have to enter 10235. That is correct. Then longitudinal. So in this case, we don't know which direction longitudinal because pump is in horizontal direction. Okay. So they consider Fy as longitudinal. Okay. So they consider Fy as longitudinal and they given 6007. But whatever axis you are giving here, that should be your longitudinal. Here they given wrongly. Maybe your axis you have to change it to like this, or your equipment direction, which equipment is located. For pumps, we don't have particular direction. No, the pump is in the same direction only, so we cannot give. So either you have to give vertical or this Z direction. Either you can give on the vertical. So I have to give 1 here and here 0. Then whatever they given, it is correct. Okay. And then other axis is Z axis, that is 6675. Okay. Then same way moment also we need to give moment longitudinal torsional moment, that is 1763. Fx is equivalent to mx and Fy is equivalent to my, that is longitudinal, that is we are given 420 here, and mz same way, both values are same, just we have entered the value. So like this only we need to give, we need to consider the forces and moments, we need to give it in this one, the nozzle limit check. Then you run the system the same way what we have done using Excel sheet, no? The same way only we are going to check. But in CAESAR itself, no need to do this manually, the values and all. So you will check in the CAESAR itself, the output. You go here, T2, T3, T4, T5 and this one. Now we will see only the pump. Nozzle check, check, nozzle check. Select nozzle check and wave report. So you see, so all nozzles are qualified. Means our pump nozzles, if you see, these two are pump nozzles. The pumps are qualified here. Uh, Whatever we are given, this is that one. Longitudinal axial force, longitudinal force, circumferential force, torsional moment, circumferential moment, longitudinal moment. Okay. So you see the force check, it is compared with each and every case. So it is showing the result. Okay. So individually it is showing the result. It is 29.4%. It is comparing the result with the allowable. So the result is 29.4. So all or pausing. Yeah, it is 80%. So maximum is 80%. So it is okay. How the 80% achievements? The maximum value only it will show. 340 divided by 420. This is the value it is showing. Okay, 340 divided by 420. So that is the 0.809 value. That is into 100 and 80.9%. If it is within the within 1 minute, it is okay. If it is more than 1, it will show in red color. Okay, so both pumps are clearing suction, and for the vessel, you need to include this one also. Design temperature also. See, in the vessel, it is exceeding marginally. You see, 1500 is allowable, and sorry. So your load is coming around 1115. It is below 1% only. So it is acceptable. The client is, when the vendor has acceptable this one, accepted this one. That's why we are kept like this. So using expansion joint, we have qualified this nozzle. So like this, you can try in different way. Okay. So the next class, I will show how to reduce the loads for the horizontal vessels and all. Okay. So vendor drawing, this is very important for all the equipments. Okay. I will show you some. So like this, in all vendor drawings, it will be there. For example, if the line is connected to the shell, the nozzle is on the shell, this is shell, then you have to consider this value, individual values you can consider. Okay, FA, FL, FC. But if the nozzle is on the head, means that is on the disc end. Okay, like this. If your vessel and equipment axis is on the same direction, then what we will do? How to check? That we will see in the next class. Okay. Thank you.